Hello everyone. So today we have two examples. Both of them we have to draw Mohr circle on both of them. So they're basically Mohr circle, and we're gonna use the Mohr circle application in the first question to find the principal stresses, and in the second question we're gonna rotate this element by a certain degree, which is 44 degrees. So let me start with the first one. So we are given this element, okay, and we are first asked to evaluate the principal stresses, shear stresses, maximum shear stresses, and the principal angle. So before going through the solution, I want to write the sigma x, sigma y, and sigma moment, or no sigma moment, the tau xy. Okay, so sigma x is negative 27 because 27 is compression here, and it's megapascal. Sigma y is 20 megapascal, and the tau is negative 8 megapascal. If you remember, this is the negative sign convention for the shear. Okay, and now we can start solving for the requirements here. So first of all, I want to find the sigma average. So sigma average was equal to C, which is the center of the Mohr circle, which is sigma x plus sigma y over 2. So sigma x, it's negative 27. I'm now reading from here, plus sigma y, which is 20 over 2. And I got negative 3.5 megapascal. And this is the first point in the Mohr circle. So this is gonna be C, which is the center of the circle, minus 3.5 and 0. Okay? Second thing, I need to calculate the tau max, which is the shear, which is I'm gonna call R, which is the radius of the circle. So it's gonna be the square root of sigma x minus sigma y over 2. Common mistake that you put here plus. So this is not average, this is just minus. Another common mistake that you forget to square it. So plus sigma xy squared, and now I'm gonna say sigma x, which is negative 27, minus sigma y, which is 20 over 2 square, plus 8 square. And I'm going to get 24.82 megapascal. So now I found the maximum shear stress, and this is the maximum in-plane shear stress, which what was required here. Now I want to find the principal stresses. So principal stresses are sigma P1, which one of them gonna be C plus R, which is sigma P1, and the sigma P2 gonna be C minus R. So the C was negative 3.5, the R was 24.82, and I'm going to get 21.32 megapascal. Same thing here, I'm gonna say negative 3.5 minus 24.82, and I'm getting negative 28.32. And those are principal stresses, and those are points on the Mohr circle, and those are another points that I'm having. So 21.32 and 0, and that is sigma P1. And then I do have sigma P2, which is negative 28.32 and 0. And those are the boundaries of my circle. So if I know the boundaries, and if I know where the circle is, which is here, the center of the circle, and I know the radius, I can draw the circle, which is what I did here. So what I did here, I basically calculated P1 and P2 to know where the boundaries of my circles are. So P1 and P2. So here is P1, which is equal to 21.32 and 0. Sigma P2 here is equal to minus 28.32 and 0. So now I knew the boundaries of my circle. So once you know the boundary of the circle, that's when you can establish the horizontal and vertical scale. So what were we drawing the Mohr circle on? We are drawing on sigma and then tau. And if you remember, we're not calling tau positive and tau negative. Instead, we are calling clockwise tau, and here counterclockwise tau. So as if this side, which is supposed to be negative, we are not calling it negative, we are calling it counterclockwise, and we're drawing it like this. So it's always gonna be that way. Okay, so now what is left, we want to find the principal angle. So the principal angle is gonna be tan 2 theta p is equal to tau xy and over x minus y over 2. Also, common mistake here that you put plus here. It's not plus, it's minus. It's equal to tau xy was minus 8, then x minus y over 2, which is negative 27, minus 20 over 2. I'm going to get 2 theta p, which I'm going to say tan inverse this. I'm getting 2 theta p is equal to 18.8 degree, and the theta p itself is going to be 18.8 divided by 2, and I'm getting 9.4 degrees. So since I got the theta p positive, which means that from the x-axis to p, I have to go, so it's positive, so I have to go counterclockwise. So here is the principal plane, or the principal stress element, or the principal stress where it's gonna be. So it will be from the x, I have to rotate counterclockwise. One more thing that I need to know from this equation. So from this equation tells me two things. If it's positive, that means I'm going counterclockwise, and that's the sign convention for the theta. If the theta is positive, I'm going counterclockwise. Second thing is this theta p, the rotation from x to sigma p, or stress p1 or stress p2? How we figure out this? By looking at the denominator here. If it is negative, that means we are rotating to sigma p2. So now I know that I'm going to rotate to sigma p2, which means that if you rotate the x by theta p, that is you're gonna get the sigma p2. And this is what's gonna be verified in the Mohr circle. Finally, I want to draw, or I want to find where the reference points are. Reference points, which is the xy plane that I'm gonna put on Mohr circle. So I'm gonna say x and tau xy, and then y and tau xy. So x, you're gonna read it from here. So what we are doing now, we want to find a point on a circle. So the circle is mainly all these points on the perimeter of that circle, and every point here represent a plane. A plane means, for example, this is the stress element, and this plane that we don't see, which is like inside the page, this plane has a normal stress and has a shear stress. Any plane has a normal stress and shear stress. Any plane has a normal stress and shear stress. That's why when we put a point on a circle, we are talking about a plane. So if I want to talk about sigma x and tau xy, which is basically we are talking about that plane, this plane and that plane, which is in the x. So if I have a plane and x coming out of it, or x is perpendicular to it, we call that x-plane. So for that x-plane, I do have sigma x negative 27, which is 27 in compression. So I'm going to say 27 in compression. And I want to find the shear on that plane. So in that plane, what is the shear is trying to do in the x? So I only look at those shears, those two arrows. So if you notice that the shear is trying to rotate the x face in clockwise direction. So I'm gonna say tau, which is 8, the shear here, which is 8, I'm gonna write 8, and I'm gonna write next to it clockwise. For y, I do have, for this y face, we do have 20 coming out of it, and then I do have a shear at the y faces, and this shear is trying to rotate the element in the counterclockwise. So I'm gonna say sigma y is equal to 20, and then 8, I'm not gonna say negative or positive, I'm gonna say counterclockwise. Okay, and now I have the reference point, I have the everything now. So let's move to the circle. And this was the requirement for the first requirement here. So now we need to plot the Mohr circle and label all the important points and the XY axis or XY plane. So where is the reference point on Mohr circle? So the first point I have sigma x and tau xy. So I have negative 27, which is here, 26, so it's kind of here, negative 27. So 26 and 28, so 27 is going to be here. And then 8 clockwise. So clockwise is up. So I'm going to go from here to here. So whenever I hit the circle, this should be 8, which is, it's not, 1 minute, let me see, which is this 8, and here is 27. So here's 27, and here's 8. So this should be sigma x, and it is negative 27 and 8 clockwise. The other point I have, which is the sigma y, it is 20 and 8 clockwise. Positive 20, which is here, and then I do have 8 here. And this is sigma y, and it's equal to 20 and 8 counterclockwise. I'll make a line between them, and this line should pass through the center of the circle. So the center of the circle, this line should pass through, so it passed, okay? So this line is the XY plane or XY axis. So I'm gonna write on it, this is the XY planes, which also shows here, this is the X and this is the Y, and the relation between them, they are 90 degrees from each other, but this is 90 degrees in the X and Y coordinate, right? But in the Mohr circle coordinate, which is sigma and tau, and how we derive the Mohr circle, everything was based on 2 theta. So now the angle between these 2 points, which is y and x, it is 180 degree, which is 2 theta, which is 2 times 90 degrees, and the 90 was from the xy plane. So this is the xy plane, and now we're gonna use this reference line to rotate our element. So we have this point, which both of them makes an element and 2 orthogonal element. And now if we want to rotate to any certain point, for example, we're gonna rotate from the xy plane, okay? So now what we want to find where is the principal plane. So this line is the principal plane where we have sigma p1 and sigma p2, and the angle between them 180, which tells you those are one element and they are orthogonal planes. So this is the principal plane, okay? And now we want to find the theta p and theta s. And theta p we just calculated a moment ago using the equation, but let's find it here. So theta p is the angle from the xy plane to the principal plane, right? That's sigma p. So here we're gonna say 2 theta p, and here 2 theta p. We're not gonna say theta p only because we are not on the xy coordinate, we are in the sigma tau coordinate. So this angle from the xy plane to the principal plane, that is 2 theta p. And we calculated it and we found that it's 18.8. So you either calculate it using the equation like what we did here, or you can create a triangle here. This height is 8. Find this horizontal dimension, which is 27 minus 3.5, and just simply say 10 inverse this over that, and you should get 18.8. So that's 2 theta p. And then 2 theta s, which is the angle from the xy plane to the shear plane. So where is the maximum shear? So the maximum shear can happen at the top and at the bottom, and the maximum is going to happen at a line that passes through the centroid. So I'm going to draw a line here that tells me that's the maximum shear plane. I'm going to move it here. And this is the maximum shear. So you either eyeball it or just read it from here. So I have a maximum shear, or the radius is 24.82. So from the center to the furthest point up, that is the radius, which is 24.82. So the x value, which is the sigma value, it's negative 3.5, and then I do have 24.82, and I'm going to write next to it clockwise. At the bottom, I do have also negative 3.5 because we are on the left, and then I'm going to say 24.82 counterclockwise. This is the point, and that's the point. I'm going to call this line, that is the in-plane shear stress plane, okay, or planes. And this should have at 2 theta s equal to 90, because both of them forms a 90 degree. So I'm going to say 90 minus 18.8, and I'm going to get 71.2. Okay, now let's draw the element, or let's draw what is required here. So draw properly oriented stress element for the state of principal stress and state of maximum shear stress. So for the state of principal stress, what I'm going to find, if I want to find the state of principal stress, is I want to rotate the xy plane. If you see here, that's counterclockwise by a value of 18.8. So in this diagram, this is the x, and the x is here. This is the xy plane. So I want to rotate, this is the x point, right? So this is the x plane. This is the x. I want to rotate this x by 18.8 to the sigma p2. So now I know that if I rotated counterclockwise, if I rotated the xy plane counterclockwise like this, I'm going to the principal plane. So that's why I made it here. And I'm not going to write 18.8, I'm going to rotate it by 9.4 degrees. Okay? And now if I rotated the x-plane by 9.4 degrees, I'm going to find the principal stress element. So let's fill this graph. So x element has negative 27 in compression and 8 clockwise shear. So this x face has 27 in compression and has 8 clockwise, which is the shear going to rotate clockwise. And I rotated it to sigma p2, and sigma p2 has an x equal to 28. So this is now, I rotated by 9.4. So this face, so this two faces is related. So this is, it went from negative 27 to 28.32 in compression. So I'm going to put 27.32 in compression, and here is going to be 27.32. Okay, and I went from shear equal 8 clockwise to a shear equal 0. That's why I'll not put any shear here. It's 0. So I finished the x. Let's move to the y face. So y here, which is this y face, I have 20 megapascal, and I went from 20, when I rotated counterclockwise to go to the principal plane, I went from 20 to 21.32. So now I have tension 21.32 here, 21.32. And do I have any shear? No, because I went from here to here, and the shear is equal to 0. Now, I want to draw the state of maximum shear stress, which obviously gonna be that one, but let's see it. So I have xy plane, okay? To go from the x face to the shear face, I have to rotate clockwise by a value equal to 71.2. So from the x, I want to rotate clockwise by a value equal 71.2, but here I'm not gonna put 71.2, so I'm gonna say 71.2 over 2, which is 35.6. Now I'm going to the shear, the state of maximum shear stress. Okay, let's fill this diagram. So x, it was this x face. I have negative 27 in compression, and it went from negative 27 to negative 3.5. So here the x gonna be 3.5 and 3.5 in compression. Okay, now the shear. So I went from a shear equal to 8 clockwise, like what you see here, to 24.82 clockwise. So here it's gonna be 24.82 clockwise here and here. So I finished x. Let's do the y. So the y went from 20 to negative 3.5. So I'm gonna put here 3.5 in compression, 3.5 in compression. And then for the shear, I went from 8 counterclockwise to 24 counterclockwise. So I went from 8 clockwise to 24.8 clockwise, which is here, 24.82. And now I am done with the first problem. Okay? Second problem. So the second problem, I'm asked to evaluate the principal stresses, maximum shear stress, and the principal angle, which is what we did in the first problem. The second thing is plot the Mohr circle and be sure to label your axis clearly and plot the circle neatly. So it's basically just draw the circle. The third thing is use the Mohr circle to calculate the stresses if you rotate the element by 44 degrees. So now we are not going to rotate the element by theta p to get the principal or theta s to get the shear. No, we're going to rotate it by 44 degrees. And 44 degrees, it is mentioned here to rotate it 44 degrees in positive, and the sign convention for the angle, the positive means counterclockwise, negative means clockwise. So it's basically telling me once you draw the reference point or the xy plane, rotate it by 44. 44 is in the xy plane, but in sigma tau plane it is 2 theta. So I'm going to multiply 2 times 44. So I want to rotate this xy plane, whether it's this way or that way, I want to rotate it by 88 counterclockwise. Okay, let's first worry about drawing the circle, and then we can worry about this later. Okay, so I'm gonna use the same steps like what I did here. Write out the x, y, and tau, and just use those steps because those steps are gonna be the same to do the circle. So sigma x is negative 7 ksi, sigma y is negative 30 ksi, and tau xy is negative 10 ksi. Okay, and now sigma average, which is the center of the circle, I'm gonna say negative 7 minus 30 over 2, and that is negative 18.5 ksi, and that's the center of the circle. So the center of the circle is gonna be C, which is the center, 18.5 and 0. Okay, R, which is the radius, you're just gonna plug and chug. It's not that hard. So don't forget, I'm gonna say 7 plus 30, not minus, this is a common mistake, square plus 10 square, and I'm gonna get 15.24 ksi. Okay, and now sigma p1, sigma p2, c plus r, c minus r, I'm getting 18.5 plus 15.24 is equal to negative 3.24 ksi, and then here 18.5 minus 15.24 is equal to negative 33.74 ksi. Now let's do the reference point, x and tau xy. So this is the x phase. I'm having negative 7 in compression, so I'm gonna say negative 7, and tau xy. So the shear here is trying to rotate the element in the clockwise direction, so I'm gonna say 10 clockwise. And sigma y is negative 30 now, and the shear, which is 10, is trying to rotate the element in the y faces. Just look at the y face. The shear here is trying to rotate the element counterclockwise. So I'm gonna say 10 ccw. Okay, calculating that the principal angle, it is negative 10 over minus 7 plus 30 over 2. you're gonna get 2 theta p is equal to negative 41, theta p is equal to negative 20.5. Two information I'm getting here. If the theta p turned out to be negative, that means I'm rotating the x element in the clockwise direction because it's negative by theta p if in xy, or 2 theta p in sigma tau, which is the Mohr circle. And the second thing, did I rotate to sigma p1 or sigma p2? So now I did rotate to this one, gonna turn out to be positive, so I'm rotating to sigma p1. Here, let's verify what we did here at the beginning. We rotated the x to sigma p2, and that's what the equation told me. Did Mohr circle told me that? Yeah, look in here. If I rotated the x face by theta p, I'm rotating to what? To sigma p2, which is what here. Here I'm rotating the sigma x by theta p, or 2 theta p, to sigma p2. Here counterclockwise, here the x face counterclockwise, and to sigma p2, which verify what I did in the equation. Okay, so now I knew that the negative 3.24 and negative 33.4, that's my boundaries. Okay, the center is negative 18.5 and 0. Okay, so this horizontal line, that's the principal plane. The vertical line here gonna be the in-plane shear stress plane. Okay, and the points here are negative 18.5 and 15.24 clockwise, and here negative 18.5 and 15.24 counterclockwise. Okay, what is missing here is the xy plane. So xy is negative 7 and 10. So where is the negative 7 and 10? So negative 7 is here, and 10 clockwise. So here is the 10, here is the 7. So this is the x. This is the x point, which is negative 7 and 10 clockwise. Okay, where is the y? The y is negative 30 and 10 counterclockwise. So negative 30 is here, and 10 is here. So if I make a line horizontally and vertically, I'm gonna intersect here. So this is sigma y, which is negative 30 and 10 counterclockwise. Make a line between them. This line should pass through the centroid because xy plane, they are orthogonal plane. So this is the xy plane. Okay, now we are almost done. The questions ask us, calculate the stresses if you rotate the element by 44. So I want to rotate this element, because xy now they form an element, by 88 on the Mohr circle, and 88, it was counterclockwise because it was positive, so I want to rotate by 88. Okay, to do so, let me find the principal angle. So the principal angle is somewhere here. It's not somewhere here, it is here, which is the angle from the xy plane to the principal plane. That is the 2 theta p. So 2 theta p, I calculated from the equation, it was 41. Okay, negative here means that if I rotate the xy plane clockwise, I'm going to the principal plane, which is what's happening here. So a negative here tells me that if you rotate the x by theta p, which is by 41, in the clockwise direction, you're gonna find the principal, right? This is what I have here. If I rotate the xy element clockwise, I found the principal plane. Okay, now if I know that this is 41 and this makes a 90 degree, so I know that this angle now is 49. Okay, so I want to rotate again from the xy plane by 88, and I already rotated here to 49. So what is left? So what is left is 88 minus 49, and my new element is somewhere here. that I want to find the stresses for. Okay, and 88 minus 49, sorry, I'm getting 39. Okay, to complete this, I have 41, 49, 39. So this angle is gonna be 180 minus 39 plus 49 plus 41, because all this makes 180 degree. So I'm getting 51 degree. So 51 degree, the angle from the rotated element, so we rotated the xy element to this new element now, this element, the angle that this element makes with the principal stress, this angle we call it 2 beta. Okay, so again, to not lose you, what we want to find, we want to find the stresses when we rotate this element by 88. So when I rotate this element, I'm having this element which has 2 points because this point is orthogonal to that point, which makes a plane, which makes an element. So I want to basically find what is the coordinate of that point and the coordinate of that point. It's not hard, it's easy. What we should do, we should form a triangle here, okay, and take this triangle out. What we know about this triangle, so this is the triangle that we took it out. We know the angle here is 51 degrees. We know the radius, which is from the center to that point, that's the radius. We know the radius is equal to 15.24. And if I want to find now this dimension, I'm gonna say radius sine theta, because if you remember the sine theta equation, sine theta is equal to opposite over hypotenuse. So sine 51 is equal to opposite, which is that guy, over radius. So I want to find this. So this is equal to r sine theta, which is this multiplied by each other, the r and sine theta. So I'm gonna say 15.24 sine 51, and I found it is 11.84. Here I'm gonna say r cosine theta, which is 15.24 times cosine 51, and I'm getting 9.59. Okay, so let's move this triangle, and I know that this height now is 11.84. So I found the second part of that point, which is 11.84. Should I put 9.59, which is this horizontal distance, here? No, this is a common mistake. Don't do that, because this is only the horizontal dimension. To get this coordinate, what I need to do, I need to add 9.59 to the center of the circle, which is, this is 18.5 plus 9.59. Now I am at that point and I can put it here, which is negative 28.09. Okay, I found that point. Now I need to find that point. So at the same triangle that you're gonna take it out, but don't do it twice because it's the same triangle. So this height this height is gonna be 11.14 counterclockwise. It's not 14, it is 84. It is 84. Counterclockwise, and then the x here. So I know that this dimension now is 9.84, which is here. This horizontal dimension is 9.84. So to find this point, so what you're gonna say, the center of the circle, which is negative 18.5, or forget about the negative now, say 18.5 minus 9.84, it will take you here, which is now negative 8.91. Okay, and those are the 2 points. So now let's draw those and represent them in the stress element sketch. So I rotated the xy counterclockwise by 88. So I'm rotating the x plane, or the x, or the xy element, because this is the element. If I rotated the x, that means also I'm rotating the y. So it's the same thing if I said rotated the x. I'm rotating the x counterclockwise by 44 to find that element. Okay, let's now fill this graph. So the x went from -7 to -28.09. So -7 to 28.09. Okay, that's the stress. The shear, it went from 10 clockwise to 11.84 clockwise also. So I'm still clockwise, so I'm gonna say 11.84 and here 11.84. Okay, so we finished the x. Let's do the y. So the y, it was -30 to 8.9, because remember, if x rotated by 88, and since x and y are orthogonal, that means we are rotating also the y by 88. So we rotated the y from -30 to -8.91. So the y is here. It was -30, then it should be here -8. Since we put it in compression, you don't need to put the signs. So 8.91, 8.91. Let's do the shear. So the shear, it went from 10 counterclockwise, okay, to 11.84 counterclockwise. And to be honest, if you know the shear already from one side, from the x, you can just continue it from the other side, but just for a sanity check, okay?
The last thing we are asked to do is to extend the concept of Mohr circle to 3D by drawing the circle for the out of plane. So as we explained in topic 20's lecture, that if I want to draw the 3D or the out of plane Mohr circle, because this one is the in plane Mohr circle because it's based on 1 and 2, and the out of plane gonna be 1 and 3, or like this is 1 or 2. Sorry, this is not 1, this is 2. So it's gonna be based on 2 sigma 2, which is this sigma p2, this is sigma p1. So it's gonna be based on sigma 2 and sigma 3, which is 0, and sigma 1 and 0. That's the out of plane Mohr circle. So if I want to draw the Mohr circle for the out of plane, I'm gonna have a small circle here that is sigma 3, which is 0, or you can say sigma 3, or it is sigma p3 equals 0, and sigma p1. That's the first out of plane Mohr circle. The second out of plane Mohr circle is gonna be from 0 to sigma p2, and that's the second circle. And as you can see, it is from sigma 3 to sigma p2, and that's the out of plane. So if you notice here, I have now 3 more circles, and if I want now to find the maximum shear, as you can see here, the maximum shear didn't happen at the in plane Mohr circle, and not at this out of plane, it is at that out of plane. So this one is the maximum shear stress. So if I want to find that point, that is basically the radius of the big circle, and the diameter of the big circle, which is, it is 0 to 33.74. So if I want to find the tau max, the out of plane, I can say 33.74 over 2. And if I did that, I'm gonna get 16.87 KSI. So this value is 16.87 KSI. And if I want to write the center, so the center is gonna be also negative 16.87, because if the whole, from 0 to the end here is the diameter, which is 33.74, the center gonna be 16.87. So I'm gonna write negative 16.87, and this guy here is clockwise. So now we extended the Mohr circle, or we extended the concept by drawing the 3D Mohr circle. So we did that. And finally, determine the maximum shear stress and whether it occurs in plane or out of plane. So as we found that the maximum shear stress, so we can write that down, for example, here. So I want to say maximum shear stress happened out of plane. And if you remember from the lecture, if I say tau max only like this, that means that's the in-plane shear stress. And to find the maximum of the in-plane of or out of plane, the maximum of the in-plane or out of plane, because now I had two maximum. I had tau max for the in-plane and I had tau max for the out of plane. So the larger of them or the bigger of them, that is gonna be something we call the absolute max shear stress, which is the bigger of or the larger of the in plane and the out of plane. And as we can see, this is our absolute maximum now. So I'm gonna write 16.87 KSI. And again, let's do this for example, question 1, although we are not asked to. For example, question 1, we have P1 here and we have P2 here. So for example, if you are asked to draw the out of plane Mohr circle or extend the Mohr circle to cover the 3D stresses, so again, sigma 3, it's gonna be 0, which is the out of plane. So we have X or P1 here, for example, sigma P1, and then we have sigma P2, which is here, which is, if I'm going to draw them in 2D, we have sigma P1 and we have sigma P2. So this face is that face. And this is P1, 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 and then P2 is P2, and then there's another P2 here. The sigma that's coming out of page, which is the out of plane here, that is going to be sigma P3, and it's going to be 0 unless mentioned. So it's by default, it's going to be 0. So now I do have the sigma P3 here. So if I want to draw the out of plane Mohr circle, I'm going to draw a Mohr circle between P1 and P3. So I'm going to connect 1 with 0, and then I'm going to connect the 0 with P2, or 2 with 0. And this is the other out of plane Mohr circle. So what you see in blue here, both of them, they are out of plane, this one in plane. So if you're asked to find the maximum absolute shear stress, so I'm gonna say absolute max. The absolute max happened in plane because P1 and P2, that's the in plane, and the maximum is this value, which is 24.82. 24.82, and that happened in plane. Okay, and that's all what I have, and I'll see you guys soon.